Can you hear me now?
Yes, sir.
Okay. Since 1997, KLM Technology Group is providing engineering, operations, and maintenance support for the hydrocarbon industry. Since 2007, we've been developing engineering design guidelines. In 2014, we renamed the guidelines to the Coleman's Handbook of Process Equipment Design. So, our core business is training, the Coleman's Handbook, process studies, HAZOP facilitation, engineering support, specialized equipment. These are the kinds of things we do. If you've searched anything on the web, you have found the engineering design guidelines. Here was the first one we did in January of 2007. And we've had some really great people working with us over the years to help do the engineering design guidelines. So I get emails from students asking for student discount. The handbook's mostly purchased by companies, so the cost is high. In June of 2014, we developed an idea to start an engineering association, utilize the handbook to train and certify individuals at a student rate. We're now in our 7th year of the association. In April 2015, we started Engineering Practice Magazine. We're now in our 6th year of publishing the magazine. First issue was April 15. We're approaching 20,000 readership per issue. I am amazed how well the readership is doing. It's doing amazingly well. So if you have an article, you should consider publishing and advertising in Engineering Practice Magazine. I'm honored and kind of amazed how well we're doing. We're doing better online than most of the major magazines. Alexa.com is an Amazon company, and they rank overall readership. Okay, so number one is the best, the higher the worst, and they're not linear. Okay, so probably the best chemical engineering magazine is Oil and Gas Journal's rated pretty highly. Chemical Engineering Magazine's rated pretty highly. The third rated engineering magazine is Engineering Practice. Some of the other ones are rated very highly. And so we're really pleased and honored that we've been accepted as well from the public as we're doing. Today we're discussing distillation troubleshooting. KLM also offers advanced troubleshooting, refinery equipment troubleshooting, ethylene equipment troubleshooting, as well as other things that can be found on the websites. We also have a series on process simulation, advanced simulation, refinery simulation, and ethylene unit simulation. So what are we doing? Introduction to distillation troubleshooting. There's a Q&A. There's a chat box. If you have any questions as you go along, you can type them in the chat box. I may get Mr. Andrew Slowly's helping us today answer some of the questions. If you wish to have a certificate of attendance, I type a certificate of attendance place to register for your certificate of attendance in the chat box. It's one of the very first things, so you'll probably have to go up to find it. Sorry about the phone issues. I've had trouble with this particular computer before's microphone, so okay, sorry about that. Let me know if you can't hear me at any point. All right, so do the simple checks first. All right, so if you're going to do a troubleshooting, what do? Well, let's do the simple checks first. So typically, somebody hires me to come do a troubleshooting. I'm going to go out, and very first thing I'm going to do is verify the tower levels. I'm going to take an operator with me, maybe a young engineer, and we're going to go up on the overhead receiver. All right, the overhead receiver's got a sight glass there, so I'm going to talk to him, and I'm going to tell him either to open the overhead to storage, or I'm going to tell him to open this reflux valve, and this overhead level should track down. We're going to go up on the bottoms level, and we're going to call in, the operator's going to call in to the board man, telling him to open this bottoms to storage, and this bottoms level should track down. What percent of the time would you guess that if you go do a tower troubleshooting, you cannot find the tower levels? What would you guess? In my career, it's always 20%. It's greater than 20%, and it's always the tower bottoms level. If the tower bottoms level is higher than the reboiler return, the reboiler will not function. You can normally install a pressure gauge on the tire bottoms line and calculate the tire level. So you have the tire pressure, you have row GH, and you can tell how high up in the column it is. So I got hired by a major tray vendor to go troubleshoot a column. And so they sent me all kind of data. The young engineers had sent me all kind of data. So basically, so I went to this troubleshooting. I was hired by a major tray company to go troubleshoot the column. So I get there. They sent me all kind of data. I did some simulations. Looked like the column should be working. So I get there and they're showing me all this data, and I said, well, let's go out and look at the column. And so I get out to the column. As we're walking out the column, the guy tells me, we don't know where the bottoms level is. And so I'm sitting there going, well, okay, you don't know where the bottoms level is. So we put a pressure gauge on the bottoms line. We lowered the level to below the reboiler. The tower started functioning. Okay. All right. Verify the tower levels. All right. The tire levels may be frothy and a higher temperature than the level egg. Because of the Bernoulli's principle, typically if you have a hot service, the level in the tower is always higher than the level in the sight glass. Okay. So do the simple checks first. The next thing we want to do is perform a tower pressure drop. Okay. Normally you can put a pressure gauge in 3 places. Right here on top of this bridle gauge, you can put a pressure gauge. You can typically put a pressure gauge right here. And you can put a pressure gauge right here at the top of the bottom sight glass. So there's typically 3 places you can put a pressure gauge. All right. You should use the same gauge, and you should read the gauge. Everybody reads the gauge difference. Okay. So same person should read the gauge. It should be the same gauge. All right. You can review the design data and know what the pressure drops across the tower should be. All right. Suppose you have 30 trays. All right. 30 trays, you're expecting a pressure drop of 3 psi or about 2 bars. What does it mean if across this tower you have a very high pressure drop? What does that mean? Well, it means you might be flooding the trays. It might mean one tray has fell upon another. Okay. It might mean it's fouled. All right. What does it mean if you have a very low pressure drop? All right. It means the trays may be laying in the bottom of the column. All right. There's all kinds of things you can tell from a pressure drop. What is the normal pressure drop across the heat exchanger? Well, now it's important for you to roughly know what these equipment design is. All right. So basically, a normal pressure drop across the heat exchanger is designed for about 5 pounds. What if this pressure drop is very high? Well, it probably means that heat exchanger is fouled. What if it means it's very low? Well, if it's very low, I may not have enough overhead vapors coming over the top of the column. Okay. In my career, about 20% of the time, you can run a pressure drop and tell what's wrong with the column. All right. The next thing to do then after that is probably go scan the column and get a better picture. All right. So you look at the levels, you look at the pressure drop across the column. So what do you do next? All right. Perform a tower temperature profile. You take a temperature gun and survey the tower temperatures. All right. So I want to survey the feed. I want to survey the tower bottoms. I want to survey the overhead temperature. I want to survey the reflux temperature, reboiler heating duty. I want to look at all of these temperatures is what I want to do. Okay. What happens if the feed is much hotter than design? Well, if this feed is much hotter than design, it's going to have more vapor and can flood this part of the column. If it's much colder than design, it can have liquid and drop off here and flood this part of the column. All right. What happens if your reflux is much hotter than design? Say your overhead cooling water is fouled. All right. So it'll come in, instead of going down the column as a liquid, it'll just go in a circle up here in your reflux. What happens if your reflux is much colder than design? Well, I can flood this part of the trays right here. Okay. What does it mean if your cooling water temperature is the same in and out? Okay. It means I probably don't have enough overhead vapor. Okay. So you can perform a tower temperature. So do the simple checks first. Okay. Verify the tower level, perform a pressure survey, perform a temperature survey. All right. So these are things to do. And most of the time, an operator should have already done this, but they don't understand the importance of doing these simple checks. All right. So you understand the importance of them. Go verify the levels. If that level is above the reboiler return, your reboiler's not going to work. You do a pressure survey. I can tell you a whole lot about a column if I do a pressure survey and I do a temperature survey. So when you're going to do distillation troubleshooting, do the simple checks first. And I'm moving way too quickly here. After you've done the simple checks first, then begin to look deeper. Sample the feeds. Has the feed changed from the design? Well, if the feed is significantly changed from the design, you end up, this tower may no longer have the proper hydraulics or have the proper number of trays for the new feed. Build a mass balance around the column. All right, so I need to look at, does it mass balance? Okay, if it's normal flow meters are within 2 to 5% accuracy. Again, that's something you should know. So build a mass balance. So you should be able to calibrate your meters and get them to within 2% accuracy. All right. So time you do 3 or 4 meters, 5% is a good number. All right. You can also do a component balance. If I've got ethane and propane, I can do an ethane balance. What goes out the top, what goes out the bottoms. Okay. Performance simulation. All right. So a lot of people jump to performance simulation first. All right. So what we want to do is we want to do the simple checks first, then come and do the simulation. You have the pressure profiles, you have the temperature profiles, you got the sample of the feeds and the products. You can now perform a simulation. And you can look at the hydraulic profiles. All right. So you have the hydraulics of the trays. So you want to look at, are these trays now designed for that simulation and for that new hydraulics profile? All right. Performance simulation. What simulation tool should you use? In the October 2017 Engineering Practice magazine, a team of 6 people rated 9 different simulation programs. So we looked at a whole group of things. A team of 6 people, and so the biggest rating difference was in the time of the simulation. All right. So some simulations converge very quickly. Some take a long time. So I would go back, if you're interested in simulation, I would go back and look at this particular copy of the magazine. The magazine can be found at iecpe.com/magazine. So this is an interesting paper. It talks about multiple simulation packages. What are the strengths and weaknesses of each? We only talked about the strengths of each, but if I didn't list something as a strength, it probably was a weakness. So you can back the weaknesses out of the paper. Do the simple checks first. Sample the feeds. Build a mass balance. Perform a simulation. All right. So these are simple things to do in a troubleshooting. So I was fortunate to work in a refinery in Houston from 1979 to 1995. Met some really good people when I worked there. Probably big chunk of you were not even born in 1979. But around 1990, they had an FCC turnaround. So the FCC was working fine. Everything was working great. They had a turnaround. Restarted the FCC, but the debutinizer column was not meeting specifications. The column was not removing the C4s, leading to the gasoline being off spec. So basically, what you've got is you got gasoline, which is a major component of the FCC. You put it through the debutinizer column to remove the C4s, but it wasn't removing the C4s, so the gasoline was too light. So they did troubleshooting, decided to shut the tower down and inspect the trays. Well, that makes sense. It was working well before I shut it down. We did a turnaround, and we might have not put some trays back in correctly. We might have done something wrong on the startup. So, basically, we decided to inspect the trays. Inspected the trays, shut the whole FCC down, which is a big unit. We inspected the trays. We found nothing wrong. So they started the FCC back up. But the debutinizer column was still not meeting specifications. They called the FCC licensor. They then inspected the column. They did some troubleshooting, and they recommended retraying the column. They recommended multiple downcomer trays. Multiple downcomer trays you can install with close tray spacing, increase the number of stages, and increase the ability to fractionate. So it wasn't a bad idea to install the close tray spacing. Okay? So, you know, it kind of makes sense to install this. All right, so they fast-tracked the tray fabrication. We shut the FCC down, installed the new multi-downcomer trays, restarted the FCC. But the debutinizer column was still not meeting specifications. So my boss, who was the plant manager, asked me to go look at the debutinizer. I studied distillation and had revamped a few columns successfully. Andrew Slowly had helped me some. And so we'd had some success. And so I went down and looked at it, but I really didn't want to look at this debutinizer very close. Everybody had looked at it. I mean, they had shut the FCC down twice. They had shut it down and retrayed it. Nothing they were doing was working. Young engineer Russ Smith was walking around the unit, was looking at the debutinizer. I talked to Rusty about every 2 months. I talked to him probably 2 weeks ago. So he's walking around the unit. He fills the inlet cooling water to the debutinizer condenser and the outlet cooling water. They're both about the same temperature. All right. Then he goes to the control room and he sees the reflux control valve was only open about 15%, even though the flow meter was reading 100%. Now, normal design of a control valve at 100% should be about 70% control valve opening. It's kind of important. I've told you several facts in this presentation about how things are designed. All right. Okay. You need to know roughly how things are supposed to be designed to understand how to do troubleshooting. So you understand how equipment's designed. If you're going to be a good troubleshooter, you have two facts. Cooling water inlet and outlet are the same. Reflux control valve is only open 15%. What is the problem? Okay, so I have this cooling water is the same. This control valve is only open 15%. What do you think the problem is? Well, the problem is this flow meter right here is probably not telling you the truth. Okay, all right. Because this cooling water is roughly, there's no heat transfer across this cooling water because this control valve is not open very much, but the flow meter is telling you it's 100%. This flow meter is probably not talking to you truthfully. Do the simple checks first. Understand how equipment is designed. Okay. In 2001, we published a troubleshooting paper with 10 case studies with a great group of guys, Andrew Soley, Timothy Gould, and myself. It's on the website. It's called Troubleshooting Practice in the Refinery. You should probably go look at it. Okay. It's a very good paper. KLMTechGroup.com, technical articles home. You'll page down to the bottom, and there is a really good paper that talks about case studies. Okay. So now we're ready for some general questions and answers, and I see several. I can see several questions here. So let me go back up to the. Some of the questions. All right. So here's one of the questions. What happens when the feed contains higher content of the more volatile components? In the case of a biased distillate, the beer feed contains ethanol content from 10 to 11%. All right. So if my feed has higher than design, I may flood this part of the column. All right. Now, I can do a pressure drop across here, and I may have to run a little less capacity here based upon the feed. But trays can run to about 110% of design. So even though you've got a lot of capacity in a tray, and so even packing or trays can run to about 110%. So what was the original design based on? The feed can be from 10 to 11%. So if it's 1 or 2%, it shouldn't be a problem. If it's a large amount, it might actually be a problem. Okay. And the butyrizer column in my facility, we have air cooler as condenser. However, pressure control across the condenser is not effective, as a pressure control valve upstream tie point is very close to the vapor inlet towards the condenser. All right. So that can be a problem because the air temperature can vary greatly. Now, where are you located? That might be a question to ask you. But if you have big temperature swings, summer to winter, that's going to be the butyrizer column. Air condenser can be a challenge, and so I think that's a challenge. Okay. All right. So I must have went back all the way to the top. All right. Okay. All right. Well, okay. So so let's talk in general about what is the most difficult in designing columns. All right. What is the most difficult in designing columns? Okay. Is it simulation or efficiencies? Is it hydraulic design? Is it fabrication issues? Is it installation? Or is it commissioning? All right. So what is the most difficult thing in troubleshooting columns? Okay. In simulation, the hardest part of simulation is deciding what tray efficiency to use. All right. So, typically your tower simulation uses 100% tray efficiency. So, but in the field, you're never going to get 100%. All right. So you have to decide what tower efficiency to use. Hydraulic design. Me and Andrew were talking about what is a good hydraulic design. I like to see at least 50% jet flood. All right. You can design them lower than that, but I think it starts to hurt your efficiency if you get below 15%. Fabrication issues. I've seen some fabricated excellent. I've seen some fabricated not so well. Installation. I've seen challenges in installation, and then I've seen them being knocked out in commissioning. Andrew, you want to comment on what's the most difficult and what causes troubleshooting issues?
Andrew here. You can hear me?
Yes, sir.
Okay, very good. One thing you got to take into account is that when you design, either do the process design of a column or you do the hydraulic design of a tray, you might only do it once in the column's life or only look at it occasionally. Whereas you might be buying spare parts often and you might be starting it up and shutting it down lots of times. So it looks like you might have a lot of problems with startup and shutdown. But that's because you do it often, whereas you don't do the tower design that often. And I typically think the two big issues in simulation are really picking the vapor liquid equilibrium of particularly some of the complex systems, and also picking tray efficiency. From the hydraulic standpoint, um, there's differences between trays and packing on complexity of design. Certainly for packing, the issues about the liquid distributors, right? And you really, unless you're a specialist, you really shouldn't be trying to design those. You just shouldn't, because you're just not going to have the skills, and there are too many things to get in your way. The tray design, you may actually do yourself occasionally. Single pass trays aren't that hard. I don't think in terms of minimum jet flood. I think in terms of minimum pressure drop across the tray typically. And they're related, right? They're not independent things, right? It's just a difference in experience and preference. So there's a certain minimum amount of jet flow or minimum amount of pressure drop. Trays have just got lots and lots of little tricks you can do, right? Different types of weirs, different types of configurations, valves, valve types, valve weights. And again, if you're a conventional type of tray, isn't that hard. If you look for a 100% to 50% turn down type of range on a 1 or 2 pass tray, you shouldn't make a lot of mistakes. You get past that, it gets tricky, right? Multi-pass trays are actually quite tricky. When multiple pass being 3 or more, they're in fact quite tricky, and that's where I see hardware errors creep in on the more complex geometries and the bigger towers, because it's just more challenging because the pieces aren't symmetrical anymore. That would be my comment on that.
Okay, very good. So back in the chat box, we had a question about the pressure control valve. He's talking about is the bypass on the condenser. So if you have a fin fan here versus a water condenser, sometimes you'll have a bypass around that. It's called a hot vapor bypass. And what the operators like to do is they like to run this bypass too wide open, so they don't have to tune it very much. And what happens is your reflux then runs too hot. And so that ends up being a problem if your reflux runs too hot. So I would go in, challenge the operators to keep this hot vapor bypass closed as much as possible. Another question is, what is the most unusual troubleshooting that you've been to? Well, I gave you a case study where I went to one and they didn't know where the bottoms level was. I gave you a case study where reflux flow meter was not telling you the truth. And then, so what are some other ones? There was they revamped a column. They went in and wouldn't start up. It wouldn't run very well. So they scanned it. Coming out of the scan, they showed that one tray was almost totally blocked. So they shut the column down. They went in. What was blocking this one particular tray? They opened it up. They found a vacuum cleaner, a shop vac was left in the downcomer. All right. So they were vacuuming out the trays of all the trash. The guy decided, well, there's no reason to take this. There's no reason to take this vacuum cleaner out, but there was a good reason, because it didn't work very well. Another one was in Lake Charles. They had put a new reboiler in. And if you're doing stainless steel welding, you use what's called argon gas to weld stainless steel. So you typically put plugs in, and you'll put different things in place so that you don't lose all the argon gas. Well, they put the new reboiler in. They started it up. The reboiler wouldn't work. Okay, something's wrong with the reboiler. So they shut it back down. Come to find out, the welder had left the argon plug in, and so it wouldn't work. Okay, Andrew, you got any unusual troubleshooting findings?
I've got a couple. You've heard me talk about the one on a packed tower where we scanned it.
Yes.
Could absolutely never figure out what the problem was until we finally shut the unit down. We had found that the random packing rings had been delivered in plastic bags, and the installers had taken the whole plastic bag and put the packing inside the tower, still in the plastic bag.
That's great. That is great.
That
great
was in a chemical plant, and that was okay. No, that's just won't work. There have been a few others. I have seen this happen in that it was in a South America where a tower was installed, and the installers had never seen a tray before. They'd never done a job before, and this actually is a problem. That it is all everyone has a first time to do an installation, right? And you hope that person's not in charge when they're doing your installation. They looked at these things and they said, boy, these trays are going to leak. There's all these holes in them, right? And they got they tried to do a very good job, and they got some scrap steel, and they actually welded panels over the downcomer outlets to prevent the liquid from leaking, right?
That's
and
great.
You start the tower up, and of course liquid can't get through it.
Right.
And these, you don't see anything this bad more than, say, once a year, once every couple of years. But you certainly remember them when you do see them.
Right. So I designed a column for a company in Thailand, and so whenever I design something, it's got a lot of safety, and so we go there, the company builds it, and I go help start it up, and I got a process guarantee. It's supposed to remove these C4s, and so I get there and we start it up. It starts up pretty good. It runs pretty good, but it won't make specs, and it just would remove the C4s like I wanted it to, and it was not a difficult column. I had example columns, and I put more trays than the example column I had, and then I put more reflux than the example column, but it just wouldn't remove the C4s. So I said, well, maybe we upset it when we started it up. But before I shut it down, it had a feed to bottoms heat exchanger, and so I said, well, let's sample right here at the bottom of the column and see what we got. And we sampled right at the bottom of the column, and it was on test. And the feed was leaking into the bottoms. And so there's always the possibility of what are some troubleshooting issues. And then there's the challenge between trays and packing. Okay, so packing has some troubleshooting challenges. Trays have some troubleshooting challenges. Packing acts extremely like a filter, and so any trash that you're going to get in it, you're going to build up a high pressure drop, and of course the packing's not going to work very well. Trays can be fouled, and so there's different things between trays and packing. And Andrew, you want to comment on that?
Yeah, the packing comes in a variety of sizes, of course, and types, and some of them are fairly tolerant to dealing with solids. Others are just great filters, right? The in general, solids containing systems that have a lot of solids in scale and are never good. I mean, trays are not really, neither trays nor packing are really meant to handle solids. There are some services, for example, like polyvinyl chloride strippers, where you actually do have solids deliberately present in the system in very high concentrations. And they're really kind of a challenge. I mean, you do need to strip them. And the selection in that service happens to be trays typically. Um, it, if I have solids present and I know I have lots of solids present, I'm probably going to use, unless I have a really good reason, otherwise I'm going to use trays, right? Simply, and try to lay them out in some fashion that'll tolerate a lot of solids present, right? Dealing with that. There's another situation that's kind of a little related to solids. It's foam, right? And I got nothing good to say about foam in your tower, whether it's trays or packing. It's just a disaster. And that can be because you have surface active chemicals or contaminants, or it's just a foam system. And that's not really a process design issue. That's more a hardware design issue. You get into this whole discussion of what's the system factor, that's called, and that's essentially a somewhat arbitrary number that's used to derate the capacity of the equipment to account for things like foam, right? And trying to troubleshoot when you have foam present is just awful, because you're never quite sure what's going on, and trying to quantify the effect of the foam is extremely challenging. The classic service that every plant everywhere has problems with is gas plants or refineries, or even now power plants with amine acid gas absorber systems. It's a notorious system for foam formation. Right. One client, I walked into the plant and they said, "Yeah, we've got 16 amine absorbers. None of them work. They all foam." Right. Um, and,
16. You'd think they would have figured it out by having 16 of them.
and it's just, and it's just, it's a terrible service, and it has to do with contaminants that get into the process, and they're extremely easy to get into the process, and they're extremely hard to remove. And they're, but there are other processes that foam too, and can't really say much else except good luck,
Good
right?
luck.
Right.
Right.
And that is another whole question. It's what the system factor is, how you derate equipment for systems that you know are going to be problems, and that's somewhat arbitrary, judgment based. I don't know. Do you have any comments on the system factor, Carl?
There's guidelines out there. There's guidelines out there like 85% for some, 60% for others. So you make the tower roughly, 15% larger or 40% larger. Typically, like if I know there's going to be foaming, I'll put a lot of safety in it. Okay, we got one more comment. Like at the pack column in their depropanizer at the facility, builds up a siphon, empties out in the tower bottoms, into the reflux drum, all within no time. Andrew's got an example of this in, I think, in that paper that I discussed, troubleshooting practice in the refinery, where they talk about a siphon building up, and it can be a challenge, particularly if you're dealing with fin fans, if they're on the ground. It's probably not a structured packing issue as much as it is a control issue on your fin fan and your overhead receiver, would be my guess.
Yeah, I would agree with that. The only commentary I have is that occasionally you see vent lines, right? The idea is it's to prevent a pocket of inert vapor from accumulating somewhere. And the location of those vent lines can create more problems than you might expect, right? And you need to pay attention to those vent lines. And if you've got this siphon problem, you might want to check. What I would do is I would check the temperature of the vent line, because they rarely ever have flow meters on them. They practically never do, right? But check the temperature, and because if there's no flow in that line, the temperature should be close to ambient, right? Whether it's a cold process or a hot process, if there's no flow, the temperature will go to ambient. But if that vent line is close to the process temperature, there could be a lot of flow in that. And when something happens that upsets that vent flow, it can upset the whole unit pressure balance. I have seen a case where the vent line on a tower preheater that went to the overhead system, right? The idea was it just would take off if they just got a little vaporization in the tower feed preheat, it would go into the overhead system and not upset the hydraulics of the feed distributor to the tower, because it was not designed as a two-phase feed distributor. Turned out that line had an enormous flow rate and no one realized it. And that creates pressure loops. And when those in parallel flow paths, pressure loops have to balance. And when the pressure on one part of the loop, pressure drop on one part of the loop changes because of a flow rate change, the pressure drop on the other part of the loop has to compensate. And you can get some surprisingly large inventory movements in these type of systems. These tiny little exchange event lines are not really innocent things, and they're very common in overhead systems to prevent buildup of inert gas pockets in the system. And you really might want to investigate those if you've got siphoning. It wasn't one of the things, and another person both Carl and I have worked with, his name's Daryl Hansen, he works for Valero. He had seen one of these where the overhead vent line of the overhead system caused massive swings in the liquid level in the overhead drum that you just absolutely would not have expected.
Okay. So thanks, guys, for listening today. There's a link if you want a certificate of attendance. If you send me an email, I'll post I'll send you a copy of the slides. We'll probably edit the presentation, and at some point we'll put it on YouTube. I have a YouTube channel, Carl Coleman CPE, on YouTube, and so we'll edit the presentation, and then we'll put it on YouTube at some point. All right. So thanks for stopping by. I think you got 82 people came, and thank you for your time. And send me an email if you have some additional questions. Send me an email. We'll can't do a big study, but if I can answer questions quickly, we can do that. And so I want to thank Mr. Slowly for helping us today. He's always a longtime friend, and he always brings a lot of good value. And so at some point in the future, we're going to invite Mr. Slowly to do a webinar for us. So thanks for your time. Be sure and go look at Engineering Practice Magazine. If you want to write an article, I'm looking for articles in the Engineering Practice Magazine, and we're getting great readership. And then we want to continue to have great articles, and we're going to try to do one webinar a month. Next month, we're going to have a gentleman that's writing a lot of articles for us talk about refining, and Dr. De Silva, and so he's a really good guy. So thanks for your time today, and thanks for dropping by. All the best.